These are essentially multiple slits on a little screen. When I say multiple slits, they are up to 1,000 lines per millimeter. They're numerous on these little slides. The grading formula here is d sine theta equals m lambda, m being a whole number of, so just a whole number where reinforcement occurs. So lambda is either 1 wavelength, 2 wavelengths, 3 wavelengths, and so on and so forth. We talk about these if we're looking at a spectroscope, and I'll just bring up a picture of the spectroscope. What we do is we rotate this thing on the table. Whoops. Here we rotate. We have what is called the collimator. It's got a single slit at the end. We're viewing a light source. The collimator is fixed. A diffraction grating is set up in the center. One of our spectroscopes here has plasticine to hold the diffraction grating. That's sufficient. The other one actually has a slot for it to sit in. This eyepiece and telescope rotates, okay, so it can move around. And on the table here, we have increments of degrees. So what we can do is we can, of course, the straight through, if we had the telescope around here, parallel to the collimator, to the center line of the collimator, straight through, we would see what? Looking through the eyepiece. Yes, we would see a central maximum. And that central maximum is just a bright band, a very fine bright band. As we rotate around, we move around looking through the eyepiece all the time. We'll rotate around to some point, depending on the wavelength of the light, the number of, or the spacing of the diffraction grating, D. We'll see at some angle as we move around another bright band, and that bright band has the name first order maximum, isn't it? And that corresponds to what when we're talking about M? What's that, sorry? Yeah, path difference of 1. And so when we have a path difference of 1 wavelength, then we have reinforcement occur. It's where the first order maximum occurs. If you take your eye off the eyepiece and have a look at how far around in degrees you have moved, you record that measurement. And you might do it twice, in fact. You might actually go from this side, find the first order maximum, then rotate around to the other side and find the first order maximum. Theoretically, they occur at exactly the same angle. And maybe you have one at reads 17.4 degrees, one reads 17.6. You would take an average of the two. Is good experimental procedure. Okay. And we talked about viewing white light in a diffraction grating. This is something like looking at the edge of a CD or the base of a CD. You see all of the colors of the rainbow because a CD has scratches in it, or a spiral scratch that shows interference of white light if you're holding it under the white, in the sunlight or under fluoro light, essentially white light. You'll see all of the colors of the rainbow reinforced. And if we're viewing through a diffraction grating here, here's our diffraction grating and our slits, then we see reinforcement of the violet line first. Why is that? Because it has a smaller wavelength, doesn't it? Yeah, exactly. Thank you. Violet. Then we go blue, green, yellow, orange, red. As we rotate around, this is the first order spectrum. We rotate around, we get the second order spectrum where M equals 2. And you'll notice it's the same sequence of colors, but it has a wider spread. Third order spectrum here, according to this diffraction grating, overlaps the second order spectrum, in fact. All right. We did a couple of problems, and I think we're going straight into some problems today, if I'm rightly so. So here's a situation where we find the angular position of a reinforcement line or a first order maximum or some M order maximum. Diffraction grating is ruled with 4,000 lines per centimetre. It's written on those little slides how many lines per centimetre, sometimes how many lines per inch if it's an American slide. You'll have to do the conversion. Find the angular position of the third order maximum when monochromatic light of wavelength 540 nanometers is viewed through the grating. Here's how we find D. 1 on 4,000 centimeters is D, which we change to meters, of course. D sine of theta is equal to m lambda. So we're talking about the third order maximum. So m is equal to 3. Lambda is given at 540 by 10 to the minus 9 meters. And we find this angle of 40.4 degrees. You can actually, if you're using a spectroscope and you know the wavelength of the light that's coming off of the LED, for instance, you could do these theoretical calculations and just confirm with your measurements. Determining the wavelength of the light here. So we rearrange this d sine theta equals m lambda for lambda. We're given D. We know the angle in this case, and we know that M is equal to 2 because we're looking at the second order image. Notice how they keep calling them different things. Second order image is not used that often. Second order maximum, second order reinforcement line, second order image, all the same thing. You know what you're looking at. I think, what do I want to do here? Oh, no, we'll do this first. So using a grating to measure the wavelength of the source of monochromatic light. Here's our spectroscope, different apparatus again. This is an overview of the spectroscope, which you have seen a few times now. I'll just skip that for now. Might not be big enough, just make it a bit bigger. The spectroscope. Or spectrometer, spectrometer. Different names for the same thing. Well, actually, a spectrometer is another type of device that measures wavelengths of light as well. But we won't talk about that now. We'll just stick to what we need to know at this stage. Essentially, what we have is here, this is a table with increments on it, degree increments, a table and you'll see them around the edge. Right here is 0 degrees, and you can rotate either way, of course. This telescope and the eyepiece rotates, of course. This side is fixed. The collimator has a slit, a single slit at the other end. What would be the width of this slit, do you think? And what do you think it'd look like if you looked in at the end? What's that, Matthew? It's not a hole. It's a slit. Very, very narrow slit. So narrow that it just looks like a very fine black line. Very fine. Very sharp pencil line. Okay. And that is because that width for diffraction to occur as the light goes through the slit needs to be of the order of the wavelength of the light, which is 10 by 10 to the minus 7 meters. All right. Very, very small. That light diffracts through the slit, strikes the diffraction grating, and then we view at various angles the light that reinforces. Okay. Um, inside the eyepiece, uh, we have crosshairs. And you might see, this is what you'll see. You won't see it all at once. You'll see just an area of it. Oops. You'll see, imagine this is the view in your eyepiece. I can't draw circles, can I? If you're looking through the eyepiece on the straight through position, that's essentially this area here is what you would see. As you rotate around, rotate, you're going to see a whole lot of blackness for a while, for a few degrees, depending on D and the wavelength of the light. And then what you'll do is this first order maximum will become apparent, and you'll also see crosshairs that look something like this. And the idea is that you align the crosshairs with the center of this reinforcement line, and so you can get it. You can measure the angle from the central band to the first order maximum very accurately. Question? No. No. Okay, that's fine. Yep, easy. Am I talking too much? Is that too? Everybody understands? Good. This is what you see. If we have a laser, and we talked about, we already talked about the laser, the idea of if you're measuring a laser. I won't do it all again, but imagine you have. Imagine you have this. This is your laser line here, and what I tend to do is I point it to the board, and we could put something here. What could we put here to get the laser to diffract and interfere? You can put a double slit. Put double slits there. Which we have described before, or a diffraction grating. And wherever your screen may be, and your screen's going to be the whiteboard over here somewhere, what you'll see is you'll see this whole thing, because the whiteboard's big enough, hopefully, and you'll see, of course, your central maximum, and you'll see your first order maximum, your first order maximum, you'll see your second order maximum, and your second order maximum. And if you know the distance between the diffraction grating and the board, and you measure the distance from there to there, and the distance from there to there, and so on. This distance, of course, we would call L. This distance here, we would call D, each of these. Sorry, delta Y. We can very accurately measure this, L, and we could very accurately also measure this distance between the reinforcement lines. And if we know that with some simple geometry, you can actually work out the angle at which that reinforcement line occurs. So if I take a central line and that central line has length L, okay, we can actually work out this angle theta. Okay. With some Pythagoras, because we'll just assume that of course, is a right angle. Sorry, trigonometry, SOHCAHTOA. Um, lambda equals, we're not sure. Because these angles are quite large, these distances will be quite large and the angle will be relatively large. The measurements are quite precise because you're measuring, if you're measuring millimeter accurate, then you're very close to the order of, your text will say 0.1 of a degree. Okay, so you can be very accurate with this if you're very careful, very carefully measuring. Then you would use this d sine theta equals m lambda to find your lambda, because you know what this value is for m. You know the slit separation, and you can measure sine theta easy enough. You can measure theta easy enough. You can be very accurate. Careful measurements. Careful measurements will give a very accurate value for lambda. I'll move it back up in a second. Here's a problem for people to have a go at. Finding the maximum number of orders of reinforcement observed. What's the limit here of how many lines of reinforcement you could see? Why? Why 3? Oh, well, imagine this board went on to infinity. Yeah, remember that these are, yeah, they do. Their intensity reduces as we move out, don't they? But also, what about this angle theta? What's going to happen eventually? Yeah, that's right. It'll reach some point where it reaches 90 degrees, and then you're not going to see any reinforcement, of course. Um, so sine of theta is going to be less than or equal to 1. That would be your limit. That's a clue to this first question. Diffraction grating is given 4,500 lines per centimetre. The wavelength of the light is given. Find the maximum number of orders, how many of these there are, of reinforcement that can be seen through the grating, firstly. So we'll have a look. We'll do our conversions first. We'll find our D, our value for D. Uh, D is equal to 1 on 4,500 centimetres, which equals, we'll just go straight to the metres. We've done this a couple of times, 2.22. 2.22 by 10 to the minus 6 metres. Good. They give us our lambda equals 589 nanometers, which equals 589 by 10 to the minus 9 meters. Maximum number of orders. What information do we have here? Yeah. So, okay. So if you say that d sine theta equals m lambda, this is how big does this go? This m is the question, isn't it? Really? Sine of theta equals m lambda on d, and we can do this calculation, this lambda on dm. Okay, so 589 by 10 to the minus 9 on our d, 2.22 by 10 to the minus 6 m, which comes out at 0.265. 0.265 m. And remember, this is sine theta here. This value here is important because I can say now, if I leave that there where it is, I can say sine of theta is equal to, no, sorry, it's going to have to be less than or equal to 1, because where theta equals 90 degrees, okay? Because at 90 degrees, we're not going to see anything. As theta, as this theta here approaches 90 degrees, of course, we're not going to see any reinforcement out this way, are we? We might see it out here, yeah, 89 degrees, if you had a board long enough, but it's unlikely. We'll just go for the maximum, though. That's at the point where it approaches 90 degrees, less than or equal to 1. So where is this less than or equal to 1? 0.265 times 3 is equal to 0.795. If we go 0.265, this is trial and error, by 4, we get over the 1, don't we? Okay, equals over 1. This value 1. So, what's that, sorry? Yep. Rounded down, yeah, it's another way you could do it, absolutely. So, whole number of orders, yes, we would see is 3. So if you get a value of 3.75 in 1, divide 1 by this number, you get 3.75. Is that right, Alan? Yeah, 3.77. 0.77 isn't a whole number of wavelengths, is it? So maximum number of orders is 3. Number of orders is 3. The question, and then the second part of the question says the maximum number of maxima that will be observed. Here's what we're seeing, isn't it? We're seeing, so we've said that we see 3 orders maximum. How many bright bands can we see? 7 in total. Can you see that from that diagram there? We get a central band, our 3 orders on the right-hand side and our 3 orders on the left-hand side, matching each other. For 2, maximum number of reinforcement lines equals 7. Yeah, so dividing 1 by this number, then it's probably a quicker way than using trial and error. One more question. If nothing else, we can prepare for the next lesson. Actually, I think there's 2 more. Yes, there's 2 more. Example 8. Have a think about this. To show that the second and third order spectra of white light overlap. Show that the second and third order spectra of white light will overlap when viewed through a diffraction grating. Take the wavelength limits of white light to be 400 nanometers and 750 nanometers and refer to the diagram in 10.23, which would be this one here. Yes. Have a look. Second order spectrum and third order spectrum. How do you show mathematically that they do overlap? Thank you. I'll see you tomorrow.